recently one-upped Near. It's the first spacecraft to ever land on an asteroid and then return to Earth. It arrived in June 2010 after a 4 billion-mile round trip.
As planned, most of the spacecraft burned up in the Earth's atmosphere, but the sample return capsule successfully landed in the outback of Australia.
Even today, it's still unclear if minute samples are present. The careful examination of the capsule is continuing.
It's a long process, but people are optimistic that we're going to get great data out of the first asteroid samples returned to Earth.
To a geochemist, a couple of micrograms of material is plenty to do some detailed chemistry and mineralogy and compositional work.
Even before Hayabusa returned, another asteroid mission was already underway.
3, 2, into ignition, and we're going.
After a 2007 launch, the NASA Dawn spacecraft is on its way to 2 of the largest asteroids in the asteroid belt between Mars and Jupiter. Dawn will arrive at 320-mile-wide Vesta in 2011, orbit for a year, then reach 600-mile-wide Ceres in 2015.
You couldn't find 2 asteroids more different from one another. Ceres is thought to be relatively wet, perhaps subsurface ices. And the other one, Vesta, is thought to be the opposite. It's completely lacking in hydrated minerals or water ice. It's been heated over its lifetime to such an extent that it's thought to be layered. A surface layer, a mantle, and a core, much like the Earth.
All of these missions are revealing that asteroids are made from a much wider assortment of materials than we first realized.
There's a huge variety in asteroids. Some of them are iron-rich or nickel-rich, very much like this iron dumbbell. Others are very similar to this earthbound rock. They're stony, they're rocky. Still others are a combination between the iron type and the stony type. We've also got exotic things like rubble piles, which are like having this handful of gravel, but if it all were gravitationally bound in a big asteroid kind of a form. We also have X-comets. And X-comets have gotten rid of all their ices, and we're left with this fine-grained material held in a very porous type fluff ball.
But asteroids are surprising us in other ways besides their composition.
The Galileo mission on its way to Jupiter went past an asteroid called Ida and discovered that it had a little tiny moon called Dactyl. This was a big surprise, and now we see that that's not so rare an incident. Asteroids do come with their own moons, sometimes several moons.
We're also learning that a lot of asteroids are traveling in pairs, as binaries, or even with 3 of them. And that's a very new set of observations and a new thing to understand.
Knowing how asteroids are grouped and what they're made of is more than a matter of scientific interest. Imagine in the future that an enormous, deadly asteroid is speeding towards Earth. It needs to be deflected if mankind is going to survive. But if we don't know exactly what the asteroid is made of, then the effort to save the planet could go horribly wrong. An asteroid impact can unleash more destruction than just about any other kind of natural disaster. But it's also one of the few types of nature's fury that we may be able to prevent. Imagine in the future that a huge asteroid is racing towards Earth at 70,000 miles per hour. International space agencies have banded together and launched a rocket in an effort to save mankind.
The trick is to understand the enemy. Is it made of solid iron? Is it made of shattered rock? Is it made of a rubble pile, an exclamatory fluff ball? Because if you hit a slab of solid iron with a spacecraft, it's going to react far differently than an object that is a fluff ball.
The asteroid turns out to be a rubble pile. It's soft enough to mostly absorb the impact of the rocket and to stay on course to collide with Earth. It's also large enough that it doesn't burn up in the atmosphere. It hits and forever changes life on our planet. This is the price we could pay if we don't learn as much as possible about the variety of asteroids in our solar system. But at least with large asteroids, we should have years or decades of warning about their approach. With comets, even enormous ones, the warning time will be measured in months. Why? That's what Clayton L. in Atlanta, Georgia, wanted to ask the universe. So he emailed us. Why would there be so much less warning time before an Earth impact for a comet compared to an asteroid?
Good question, Clayton. We'd love to know when something might hit us. It turns out that asteroids are so nearby that we can track their orbits precisely. That means we can make accurate predictions of where they will be, tens or even hundreds of years in advance. That means we might be able to deflect them before they hit the Earth. Now, a comet comes in from the outer depths of the solar system and doesn't become bright enough to see until it's maybe 6 months or a year away from hitting us. So we have very little warning. Fortunately, most of the things that potentially could hit the Earth are asteroids, not comets. And we can track the asteroids pretty accurately.
The fact that asteroids have a much greater chance of destroying life on Earth sometime in the future is one of the main reasons why studying them with unmanned missions is so important. But in April 2010, US President Barack Obama announced an even bigger challenge.
By 2025, we expect a new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. So we'll start by sending astronauts to an asteroid for the first time in history.
In my experience as a college teacher, the younger generations, they want to go beyond. Yeah, my grandparents went to the moon, you know, let's go beyond. And so that was an inspiring part of the president's message, that we need to get NASA back into the business of deep space.
A manned mission to an asteroid will be very different from moon missions of the past. In some ways, it will be easier, and in other ways, much harder. Whichever asteroid the astronauts visit will likely be a lot farther from Earth than the moon. So the journey will probably last for months instead of the 8 days it takes to get to the moon. But the round trip will actually use less fuel than a lunar landing mission.
When you go to the moon, you're dealing with a body with significant gravity of its own. You're having to use more fuel to safely slow yourself down and descend all the way to the surface. When you head to an asteroid with very low gravity, even though you're going farther to get there, you aren't having to expend nearly as much fuel for things like getting to the surface. It also takes less propulsion ability when you leave the asteroid to head back to Earth.
But landing on an asteroid's surface will be much more challenging than setting down on the moon.
It's more like docking than it is landing. But you do have some gravity, so you have to deal with having a little bit of gravity. But you have to deal with actually anchoring yourself, holding on. You don't have to hold on when you're in the 1/6 Earth gravity of the moon.
Exploring a small rotating asteroid will also be much harder for astronauts than hopping around on the moon. It'll be more similar to a spacewalk.
Your sense of up and down is sort of screwed up. And you have to be very careful when you walk around on an asteroid because the gravity of the asteroid is so weak. A good jump can send you into an orbit around the asteroid or even send you out at escape velocity and escape from the asteroid completely. So you have to make sure that you're tethered down when you're exploring.
But since rovers have already proved to be so successful at exploring other worlds, is there a strong reason to send astronauts to an asteroid?
Astronauts, explorers, the public interested in space yearn to see what it's like in person through real human eyes. And that day is coming.
Robots can do a lot and have done a lot in space exploration, but there is no better geologist than a human being. To be a geologist exploring an asteroid and being able to recognize the history of a particular region, looking at familiar types of geological formations, you know just what you want to do. You want to go sample that rock, you don't want to go sample that rock.
Asteroids are also important because of the resources they might contain. The year is 2050, and a crew of astronauts has just landed their spacecraft on an asteroid. They're not here to explore. This is merely a pit stop. But what types of precious resources could this small rocky world possibly contain? asteroid attack can wipe out entire species, including humans. But instead of accepting that fate, scientists are trying to learn enough about them to prevent disaster. And asteroids that aren't headed towards Earth may even turn out to be helpful.
One of the reasons to visit asteroids and to study them is that they may have some resources that could be useful to future human explorers. And among the most important of those would be ice, water. People are going to need ice to live and drink and use in a practical sense.
The year is 2050, and a crew on its way to Mars has just stopped at an asteroid for water and other supplies. The oxygen in the water can be separated to refill the crew's breathing tanks. But there's even more that this rocky supply station has to offer.
It's conceivable that with advanced technology, we could go to those asteroids, break down the water, and use the hydrogen and oxygen as fuel to take spacecraft even farther.
And there may even be priceless materials to bring back to Earth. Elements so rare and critical to high-tech success that they could be the cause of future wars.
Some asteroids have platinum and titanium and rare earth elements that are important in many aspects of electronics, which are called rare earth elements for a reason, because they're rare on the Earth. They might not be so rare in certain kinds of asteroids.
But the most important reason to investigate asteroids remains their ability to instantly kill millions of people. Or wipe out the human race altogether. To counter this threat, NASA launched the WISE mission in December 2009. The Wide Field Infrared Survey Explorer has already found 25,000 asteroids and more than a dozen comets that were too dark to find using visible light.
It's actually looking all around our solar system, hopefully to look at 99% of the sky and try and map more of these near-Earth objects, these asteroids that we haven't found in the past. And hopefully that'll help us in understanding if there are any that are in near-term collision courses with the Earth.
And even though it doesn't usually make front-page news, there are already plenty of asteroids that pass close to Earth. In April 2010, a 70-foot wide asteroid passed within 220,000 miles of Earth, which is closer than the distance from the Earth to the Moon. And a few months before that, a 23-foot wide asteroid came much closer.
In the winter of 2009, in November, there was an asteroid that passed so close to the Earth, it was only 8,000 to 9,000 miles away at its closest approach. And we didn't know about that until we got fairly close.
That's about the same distance as flying from Los Angeles to Mumbai, India. And back in 1972, a tourist's camera near the Grand Tetons in Wyoming captured a much closer pass by a similar-sized object.
The 1972 event was about as close as you can get to a collision without actually colliding. On its way in, it was going to collide with the Earth, but it skipped off of the atmosphere due to the pressure of the air, like a pebble being skipped off of the surface of a lake. That was a really close call.
Then, in October 2008, a small and seemingly uneventful impact occurred in a remote part of the African country of Sudan. But it actually represented a giant step forward in the science of predicting asteroid impacts.
A small asteroid was discovered, and it was predicted to land in Sudan the next day, and it did. Now, this is the first case we have of an object that was discovered and then predicted to land at a particular time and place. And in fact, fragments of this object were later found over the desert.
But that was only a small impact with a single day's notice. Today, the jury is still out on whether we'll be able to identify and deflect something that could inflict catastrophic damage on Earth. Scientists believe there are still millions of unidentified asteroids out there capable of destroying a city. Or worse. Will we be able to figure out which ones will cross our path? And will we be able to prevent them from slamming into Earth? The stakes couldn't possibly be any higher. Each Each new discovery in the world of asteroids isn't just a scientific advance, but an opportunity to increase the survival chances recently one-upped near. It's the first spacecraft to ever land on an asteroid and then return to Earth. It arrived in June 2010 after a 4 billion-mile round trip.
As planned, most of the spacecraft burned up in the Earth's atmosphere, but the sample return capsule successfully landed in the outback of Australia.
Even today, it's still unclear if minute samples are present. The careful examination of the capsule is continuing.
It's a long process, but people are optimistic that we're going to get great data out of the first asteroid samples returned to Earth.
To a geochemist, a couple of micrograms of material is plenty to do some detailed chemistry and mineralogy and compositional work.
Even before Hayabusa returned, another asteroid mission was already underway.
3, 2, engine ignition, and liftoff.
After a 2007 launch, the NASA Dawn spacecraft is on its way to two of the largest asteroids in the asteroid belt between Mars and Jupiter. Dawn will arrive at 320-mile wide Vesta in 2011, orbit for a year, then reach 600-mile wide Ceres in 2015.
You couldn't find two asteroids more different from one another. Ceres is thought to be relatively wet, perhaps subsurface ices. And the other one, Vesta, is thought to be the opposite. It's completely lacking in hydrated minerals or water ice. It's been heated over its lifetime to such an extent that it's thought to be layered. A surface layer, a mantle, and a core, much like the Earth.
All of these missions are